Swayam Prabha. Digital India. Educated India.
Welcome to our lab. So we are working on electrochemistry and corrosion as our base, and we are focusing on keeping this as our base, and we are covering multiple applications. So here I am going to just show a laboratory version of how the things will work based what sir taught us in the morning. So what sir taught us, like Rajanambat sir taught us, is about the green conversion coatings. So there are many coatings, then why we are going for green conversion coatings. So that's from that we will start. So like, can you list some number of coatings, like the types of coatings that are existing, like one by one, like can you list? Method. Electrochemical, like yeah, PVD, CVD, so thermal spray, then anything else? Polymer coatings, yeah, electroplating, electrodeposition, yeah, like galvanizing, all these are the different types of coatings that are existing. So what is the purpose of coating? Like why we need a coating over a metal? Like, yeah, barrier, sorry sir, I could not hear you. It's a barrier coating. So why we want a barrier? To avoid the communication between the environment and the metal substrate. So this barrier won't let you to immediately communicate your environment with the metal, but it's not like it will never like allow you. So for that many protective coatings are there, namely galvanizing. We will take galvanizing as an example. Since galvanizing, you know, right, it's a zinc deposition over a metal substrate, any type of steel. So when there is a galvanizing, then why we are going for another types or other types of coatings? We can stop with galvanizing, right? So we are having some issues. What is that is the zinc, which is getting continuously dissolved, could not able to control the underlying substrate for a longer period. For that, what is the technology which is we are bringing out is incorporating inhibitors. As such, inhibitors dispersing in a solution. But dispersing as such inhibitors is not increasing the lifetime, because once your inhibitors are getting consumed, when there is a susceptibility of corrosion, that place is becoming porous. So what it is creating is, it is making your metal or the moisture to get into the metal substrate more easily than a galvanizing coating. So we are modifying those inhibitor conversions in a separate way. So to cover this, like that part we don't want to go, since it is covering a different part that actually I am working on. What working on is smart coatings. So we will come in the other direction. So to avoid these kind of things, what we are using is a conversion coating. In that basis only chromium conversion coating came. So as you know, this Cr6+, which is more hazardous and carcinogenic, as we learnt in the morning class. So that is generally produced by a process called adaline. So by adaline process, you will deposit the Cr6+. We actually try to imitate that in our lab, since you people are coming, but we learnt about that and we got to know like it is more hazardous and we can't keep it, because disposing itself, it's a very big procedure. So we don't want to take so much of risk. So we start with green coating and we'll tell that much carcinogenic, we can't replicate as of now. So this cerium conversion coating only what I am doing. Already I started the experiment, since like it will take 1 hour to have a uniform coating. I already started due to time restrictions. So chromium conversion coating. This for an alternative, we are going to other elements. In that, one is cerium. How cerium? Because it is a rare earth element. Also sir pointed that inhibitors can be of nitrogen groups also. So in that many classifications are there through which we can take select inhibitors, but here this conversion coating is based on rare earth elements. Only this rare earth elements, as of now, like we learnt, it is observed like it can able to produce a conversion coating. So what is the difference between a normal electroplating and a conversion coating? Any guess? normal electrodeposition versus a conversion coating. Why it is like different? It is also a kind of coating. Yes sir, partly correct. But the main difference is in electrodeposition we will apply potential, either it will be a potentiostatic or galvanostatic, that is constant potential or constant current we will apply. But in the case of conversion coating, if you see, I just immerse the sample, I did not apply any potential or current or reference or counter, none of them were used, it is just immerse. So conversion coating is by immersing you will get a coating on your substrate. So that coating is more adherent, even though it could not produce as much as high inhibition efficiency like CR6 plus, but it is comparatively good coating, like as we saw 88 point in cerium, but 96 or 97 for CR6 plus. But why we are choosing is green. So that's how we are obtaining the coating. After some time I will lift the sample and I will show you. After the coating, what the characterization we will do? Like, can you name the characterizations what we will go through after a coating? Thickness, then bond strength, yes sir, yeah. Then anything, sorry sir? Resistance to corrosion. For that the study what we will go through is electrochemical study. Generally we will go through SCM, TEM for more FIB or something to know the cross section, roughness, surface profilometer, like that more things will, many characterizations are there. But here what I am going to focus is electrochemical study since we are working on that. So for any electrochemical study to happen, what we will use is a flat cell. So here we have a flat cell. So flat cell. So this I already connected that, like can you tell me the difference between that flat cell and this flat cell just by looking, visual observation? You can be louder. That is fine. More than that, anything you are observing? Yeah. So here you are having a double chamber one, and there it is a single walled one. So here you can control the temperature, but whereas there you can do only at room temperature. As we are working on like fuel cells and biomedical fields, we need to work on 80 degrees Celsius for fuel cells or 37 degrees Celsius for body fluids. So for that we need a temperature control. Since it is a normal corrosion study, I am using it in a single walled flat cell. So why we are using a flat cell? We can use a normal beaker, right? Like why we have to keep it horizontal, vertical, avoid leaking solutions. Why, like, can you tell anything why like we are using flat cell? Yes sir, it is partly right. Because if you are taking a beaker, you may assume your reference counter working are always in the same place. But it's not the thing, because human errors will make. One time it may be at different distance. So that distances will create more difference in your EIS or OCP study. So to make sure like at least the errors what we make is very less, we will use a flat cell. So everything is in a fixed position. Your working will be placed here, then your reference, your counter. So this setup will make sure like whatever the repetition study or whatever you are doing is conducted in the same sets of positions. So for that only we are using flat cell, and here what I am using is reference AgAgCl and counter as graphite. Working is the cerium coated, I am using high strength steel substrate as of now. So that substrate I am cerium conversion coating. So that is no, like it is conductive, but comparatively less, but it is conductive. So what we are seeing, no, not ceramic. So generally cerium is used as an inhibitors, anodic corrosion inhibitors. So how we are obtaining the solution is during the synthesis of inhibitor, we are taking out the extract of that solution. That solution we observed that we are getting a coating. So that coating is having a almost equivalent resistance as that cerium is produced. Then we understood that it is a conversion coating, that cerium which are dispersed or which got dissolved in that coating is still producing the same inhibition as like that cerium inhibitors which are available like powders. So, this is one form of coverage coating. Beyond on this you can have some other coatings also like paints or zinc. This is a confirmation like it is more adherent, and with this also you can leave, but the thickness of that coating may be very less, so we can't use it directly. Maybe that varies, I am not sure. So, with this electrochemical study I will go into it. So, what we will do is OCP, EIS and PDP. EIS is a electrochemical impedance spectroscopy, PDP is a potentiodynamic polarization. So, every experiment will start with the OCP. Only once the OCP is getting stabilized, we will go to the next studies, because you can't start your EIS just when you immerse the substrate, because this OCP, why we are conducting is when you are immersing a substrate, your metallic substrate will have some charge. The solution will have a distribution of charges. So, when you are immersing, the charges should get aligned, it should not disturb your setup. Like if it is unevenly distributed, you may not get your impedance or PDP or OCP in a stabilized form. So, for that only we will run OCP for almost 1 hour. It depends on metal, some metal and electrolyte. In some cases we will run for 24 hours also, in some case 15 minutes also, it will depend. Until it is getting stabilized, we have to run. So, this got stabilized by 2500 seconds only, so I switched it off. So, after that what we performed is an impedance spectroscopy. So, impedance spectroscopy is mainly associated to find the coatings and its properties. So, your coating, if it is if this is your substrate over which your coating is there, when you are immersing it for your impedance spectroscopy, what you will get is a semicircle. So, do you know, like we will get also 2 semicircles, 3 semicircles. Can you tell like why we are getting that multiple semicircles? Yeah. Yeah, exactly. So, here what I got is a only one semicircle. So, what we can generally, how we are assuming that our coating is perfect or based on just by visual observation is, if suppose you are having 2 like metal coating, if your coating is porous, what your electrolyte will understand is 2 different materials it will get in contact. So, what you will get is a 2 semicircle, because one semicircle for your resistance to resistance of your coating, another semicircle will correspond to the resistance of your metal substrate. For example, now to increase the lifetime of galvanizing coating, what people are doing is over which they are painting paint, over zinc they are using paint. In that case, if your paint is porous, your zinc is porous, easily electrolyte will touch the metal substrate. In that case, you will get a 3 semicircle thing. So, this is how we will check the coating, how the coating is. I think here it is adherent, we will assume like it is adherent and we got the same. So, based on this we will go through fitting also. We can't just like that get the parameters from the impedance. We have to go through fitting. For that some softwares are there. In that fitting you will get to know your resistance of the coating or resistance of the suppose 2 semicircles are there, how your coating is acting, how your metal resistance is varying, that difference you can get through the fitting parameters. So, this is how the impedance spectroscopy will work. I think you people might be more familiar. No sir, that is cerium coated material. Yeah. No sir, no sir, like solution and your electrolyte will be stabilized as one during our OCP. So, if suppose OCP is not stable due to the distribution of charges, it will have, we will put so. Yeah. So, here will be your working, more close to it you will keep your reference. Yeah, you will put the sample and we will tighten it. Yes sir, already it is here only. So.